Okay, so now continuing with the IoT theme, we have the team from IIT Indore of Miss Navneet Chouhan and Miss Nandini Patra. Ms. Navneet is currently a PhD scholar in the Department of Electrical Engineering, IIT Indore. She received a master's in microelectronics and VLSI design from Sri Govindram Seksaria Institute of Science and Technology, Indore, India. She's earned her bachelor's in electronics and telecommunications from NII Bhopal, India. Her research interests include optical fiber sensors, shape memory alloys coating, and hydraulic power pack monitoring. Dr. I.A. Palani is working as a professor in the Department of Mechanical Engineering at IIT Indore. After completing his doctorate from IIT Madras, he worked as a postdoc research scientist in Graduate School of Information Science and Electrical Engineering, Kyushu University in Japan. He has developed mechatronics and instrumentation lab at IIT Indore. His area of expertise includes laser-assisted surface processing, micromachining, smart materials, and shape memory alloys. He has published more than 100 international journal publications and has filed 6 Indian patents. He has executed projects from different funding agencies such as DST, SERB, DAAD, JSPS, DRDO, MHRD, worth almost 6 crores. He has closely worked with industries such as Volvo Eicher, John Deere, WABCO as a technical consultant, and has a strong research collaboration with the University of IFW Dresden in Germany, Kyushu University in Japan, and Jeju University in South Korea, as well as the St. Petersburg State University, Russia, and Purdue University in the US. He's a life member in the Indian Laser Association, RRCAT Indore, and Smart Materials and Structures, IISc Bangalore. He has received an alumni award for the year 2015 under Research and Innovation. He is a recipient of the Kyushu University Friendship Scholarship and AICTE National Doctoral Fellowship. He's a member of SPIE, Indian Laser Association, Institute of Smart Materials and Structures. He was also the founding head of the Metallurgy, Engineering and Material Science at IIT Indore, and followed by heading the Mechanical Engineering discipline at IIT Indore. Their paper today is IoT-enabled temperature monitoring of hydraulic power packs using NiTi Shape Memory Alloy Biomorph integrated optical fiber.
So good morning to one and all, and thank you very much for this nice opportunity. So I have come along with my research group. So the main focus of this work is, so we are trying to establish a sensor from the material called smart materials. So I think most of you might be aware about smart materials. So I would like to thank my guru, Professor Singh sir is there, who taught me smart materials at IIT Madras. So like under the smart materials, so under the smart materials, so we have been working on 2 main materials. One is called a shape memory alloy, and the other one is called as triboelectric nanogenerator, which is competing with piezoelectric. So we are trying to tailor these shape memory alloys and triboelectric nanogenerators for the required sensor development. Of course, like we have oriented this sensor for hydraulic related applications. So one of the application includes like temperature measurement and pressure measurement, and the other with triboelectric nanogenerators. So we have developed a vibration based sensor. So as far as this shape memory alloy is concerned, like this is a kind of a material. Okay. So this is a kind of a material which is responsive to heat. So like it works on the actuation range of something around 40 to 130 degrees Celsius. So this is with reference to nickel titanium. So in case if we need to shift the actuation temperature, so appropriately what we can do is we can make a tailor-made composition for the different application. So this work actually we did for ISRO, basically for cryogenic temperature sensing, which we have extended this work for hydraulic related application. Now, if we look into the overall response of this material, so initially it is in a, let us consider a spring. So when I try to elongate a spring, it is going to form in the form of a wire. Now when I try to supply a heat to it, it comes back to its shape. Now what we are trying to do is, we are trying to encash this displacement in the form of an appropriate thermal response so that we can use it for a continuous monitoring. And when we try to get a signal, so we can go for a predictive analysis of the temperature measurement. So the interesting part in this is we have tailored this material and we have developed this material in the form of an optical fiber sensor so that we can integrate it inside the hydraulic pack and we can go for a continuous condition monitoring. So now I would like to invite Ms. Navneet, my PhD research scholar, to discuss that, please.
Thank you, sir. Very good morning to everyone. Sir, please, can we start our presentation right from beginning? Yeah, I am Navneet Chouhan and I am going to present our work on IoT-enabled temperature monitoring sensor that we designed. Following is the walk through the presentation. And the major concerns that hydraulic system faces is about temperature, pressure, load, and variation, which ultimately results in economical loss because of degradation of the components related to it. Solution could be a real-time oil monitoring. The problem with traditional sensor is it is invasive. It has related electronic circuitry which makes it bulky and sometimes unreliable as well. With due course of time, they need further frequent calibrations as well. Optical fiber sensors are flexible enough to be implemented everywhere. They can bear harsh environmental conditions as well, and they have capability for real-time monitoring and remote monitoring as well. The concept behind is we are simply modulating the light wave guiding through the fiber, which can be modulated in the form of strain, temperature, pressure that we apply externally on the fiber. What we are focusing upon is intensity modulation based sensor, which can sense the intensity output, optical signal intensity output in form of whatever perturbations or path length changes it can have throughout the fiber. These are certain technologies will already being presented or being used in hydraulics through optical fiber sensing. Particularly, they are using FBG as a sensor or some interferometric techniques which are quite bulky and complex. They cannot be used for smart monitoring. But our concept is SMA-based optical fiber sensor, which makes it intensity modulation based, reduces complexity, ease of handling it provides, as well as it can do smart actuation. That means smart sensing. As Sir told, smart alloys can act according to temperature. It can expand and it can regain its shape with temperature while it's cooling. There are a variety of compositions depending on what temperature range you want to work. We are currently working for hydraulics in NiTi range, which is from 30 to 40 to 150 degrees Celsius. This is our evaporation technique or unit that we are using for coating the fiber, as well as we are integrating SMA coated optical SMA coating on Captain polyimide sheet that we are calling it a Bimorph through those fixtures. This is the characterizations that we did for current composition that we used, which is a quaternary based composition. And this is particularly chosen because of less hysteresis and its corrosion resistance property. As we can see, uniform grain structure is there, uniform coating is there, and the martensian and austenite phases, the initial and final phases upon heating, are lying between 50 degree to 120 degree, which is of our use. And this uniformity in structure is showing good shape memory effect property. What our structure is, we have designed a sensor structure particularly for hydraulic tank, in which the Bimorph is integrated in U-loop fiber, and when it expands, it is making the optical fiber to release the optical or increase the optical intensity. Initially, the fiber will be constrained, and when Bimorph will expand, it will proportionally expand the intensity, making it more linear within the range of our sensing temperature. This was the hot plate actuation testing that we did for our sensor, in which with Bimorph displacement, optical signal intensity was also linearly increasing. We did hydraulic power pack installation as well, in which we installed our sensor near the input and output port along with thermocouple, and externally we monitored thermal imager for sensing the overall temperature. What we observed is while during actuation of our loads, thermocouple was showing decrease in temperature because of continuous laminar flow into the tank, while thermal imager was showing that there is increase in the temperature beyond 40 degree or 42 degree. This temperature difference can be captured with our sensor, which is showing proportional increase in intensity with the increase in temperature beyond 40 degree Celsius. Therefore, with the help of our sensor, we can do smart monitoring by observing the amplitude changes. Other factors that were affecting our results were pressure and load as well, that we studied by varying different pressures and load variation, and a linear impact on VRMS value of optical signal was observed. More is the load, more the mean RMS value will increase. That means your sensor will respond more quickly towards the changes in the signal or temperature. We try to calibrate it based on some algorithm, like if we can monitor the increase in amplitude of the signal, we can directly calibrate it with thermal imager or preferably, or otherwise we can keep it on previous range only. So this is the way we try to calibrate it with thermal imager. Until unless temperature was not increasing, it was preferably held at the previous temperature only, and beyond that temperature increase was quite linear with the thermal imager. There was less effect of external factors like vibration, loading, unloading, and all these factors, which is thermocouple was very responsive to all these external factors. We tried to take those signals through IoT as well, and tried to integrate it through LabVIEW and ESP modules. They are easily captured because changes were monitored in form of voltages, which can be easily captured through ESP32 module, as well as can be directly programmed through LabVIEW for reaching our dashboards in real time. Following are the certain comparison with other sensors, in which our sensor is showing a good linearity and good significant amplitude voltage changes within a range of 40 to 120 degrees Celsius. The overall summary is that since SMA can increase the linearity of system, it can provide significant changes changes in temperature. We can integrate it with IoT as well. So there is a good scope for hydraulic real-time temperature monitoring from this sensor. And further, we will be working upon pressure and load monitoring simultaneously for multi-parameter sensing, which is possible through this sensor. Next, I would like to call Ms. Diksha for further processing.
Good morning, everyone. So the vibration generated by any machines tells a lot about the condition of the machines or any near to occurring failures. So here we are using a sensor named triboelectric nanogenerator. A triboelectric nanogenerator or a TNG is a powerful tool, as it can work as an energy harvester and also as a vibration sensor. So it works on the principle of triboelectrification and electrostatic induction. Triboelectrification is something which we feel in our day life, like that electrostatic shock we feel from our shutters or door handles. So that is triboelectrification. When any two materials having different electron affinity comes in contact like this, it causes triboelectrification, followed by electrostatic induction. When they separate, potential difference is generated, which leads to AC electrical output due to repeated contact separation. So here in this video, we can see that we have used a small TNG device of 4 cm by 4 cm. And by simple manual tapping, we are able to glow up 60 LEDs. Now we have integrated an Wi-Fi IoT module with this, so that The monitoring can be done remotely over our laptops or our mobile phones or tablet. So here the TNG is mounted over the shaker and corresponding vibration is converted into the corresponding voltage, and it can be displayed over laptops and mobile. So this is the snippet of of the live data which we are getting over the website. So as we were increasing the frequency, we are seeing corresponding increase in the voltage. And when the frequency was constant, we are seeing that constant peaks voltage signals are generating. And initially when the shaker was off, there was no input. As suddenly the shaker was turned on, we got some abrupt noise, and then we are getting a constant amplitude voltage signals which correspond to the constant frequency, and same corresponding to the turning off of the shaker. To show its application, here by strategically mapping the vibration on any machine, we can strategically position our sensor to form a machine skin. A machine skin is a customizable, self-energizing IoT-enabled sensors for condition monitoring of any machines. So in a hydraulic power pack combined with a piston cylinder arrangement, we have mounted two TNGs, one on the induction motor and another on the piston cylinder arrangement. Sorry. So here, when the motor was turned on, we will get a turn on signal on our website, corresponding signal which are being generated, and what is the vibration frequency can also be calculated and displayed over the dashboard. And when we analyze the signal generated by the TNG on the piston cylinder arrangement, whenever the piston cylinder changes direction from top dead center to bottom dead center, or from bottom dead center to top dead center, some vibration is generated. That can be analyzed. Now, analyzing this, we can detect when it is changing its direction. Now, by further processing this data and analyzing this data, we can make a prognostic model for long-term monitoring and fault detection. So to summarize, we can say that triboelectric nanogenerators are a potential device to form an array of self-energizing sensors to power IoT modules, and it can be used as an overall condition monitoring system.
Yeah. We will be further integrating these two sensors for developing a self-energizing sensor for hydraulic system, and further we will be proceeding with multi-parameter sensing at real time. Following are the acknowledgements for DST projects that we did through this sensor, the references, and thank you to the audience.
Thank you, Dr. Palani, Ms. Navneet, Ms. Nandini. It is a very good presentation. And regarding the temperature SMA, what we are using for temperature sensing, normally if you want to know the temperature of the oil in the tank, what is the heat, then we will be fixing these on the reservoir, correct?
Yes, yes.
So then the heat of the oil, whatever the temperature coming to this SMA, maybe come from oil temperature or can come from ambient or radiation, heat radiations. So how we can differentiate whatever the input output we are getting from that? How will differentiate the exactly oil temperature, or it's coming from other source?
Okay, so currently what we are doing is we are immersing the sensor inside the oil.
Okay.
Yeah.
Then okay.
So automatically it will measure the oil temperature.
So only oil temperature.
Oil temperature. And in fact, we have studied the degradation also of the sensor. So it has a long life in that particular oil.
Correct. I got clarity. Okay.
Thank you.
Okay. Over to audience.
How do you plan to commercialize this, both the shape memory alloy and the vibration sensor?
Yeah, it's a good question. So basically this, as far as this temperature sensor is concerned, so already we are in the process of packaging it for cryogenic temperature sensing. So in fact, we have established a foolproof technology with copper-based shape memory alloy for measuring up to -270 degrees Celsius. So currently the system is In fact, the product is given to ISRO. It was funded by ISRO. So the packaging process is in pipeline. So they will be integrating it inside their fuel tank. And that we will be working on it. So this is for the low temperature perspective point of view. Almost the same process we would like to follow for the high temperature applications also.
And the technology what you have developed, is it available to the public?
Yes.
Or,
yeah. In fact, the main motto of bringing this technology over here is it is available to the public. And in fact, we are looking for the industry partner also to scale it up further.
Thank you.
Hi.
Yes.
I have a question. Like you spoke about the terminologies, hysteresis and the degradation of the sensor. Another terminology I would like to put up is repeatability. How accurate is this after a certain duration of time?
Okay. So like if you look into the shape memory alloy perspective point of view, the degradation starts because of the oxygen entrapment. Okay. So because we are trying to heat it and cool it. Okay. So now we have developed a small test bed. So in that test bed, we have run this up to 20 lakh cycle in a simulated environment. So that means we apply a load to it and then we go for a rapid heating and cooling. So by employing it, we could see a degradation after 25 lakh cycle. So that degradation is not also a kind of a drastic degradation. It's a kind of step-based degradation which we have observed. Okay. So that is one point which I would like to emphasize over here. So repeatability perspective point of view, it is controlled by the manufacturing process what we are deploying.
Correct, sir. What I'm interested is repeatability when I mention, say a temperature that is measured right now is 30 degrees. After some duration, when I check with another calibrated device, the temperature would be showing 30 degrees itself. So will this sensor be able to read the same 30 degrees or will there be a delta difference in your measurement?
No, there will not be any delta change in the measurement till 10 lakh cycles.
Okay. Right. Thank you, sir.
Thank you.
Anyone else?
I have a question related to the TNG sensor. So what is the frequency resolution which we can get with it? And what about the...
Minimum we can measure up to, like we measure from 1 hertz and maximum we can go till 600 hertz right now. And amplitude wise, minimum we are able to measure around 500 micrometers, and maximum we have gone to 2 centimeters.
Yeah, actually, to add on to this particular answer, so we are more focusing on the low frequency part because you have sensors for the high frequency. So we would like to tap the low frequency. That is why we had developed this sensor, and it becomes a kind of a self-energized sensor. You don't need to add a separate power for it. So whatever it is getting generated, from that we can monitor the system.
But like, is there a scope to kind of increase the frequency resolution for this?
Frequency level, this is a kind of a contact-based system. If we need to go for a higher order frequency, then we will be going for a non-contact-based system. So Ms. Diksha has developed a magnetic-based structure, which is a kind of a non-contact, where we can monitor the high frequency, and the life cycle of it is also quite high. So that it is on a testing phase, actually.
Okay, thank you.
Yes, sir.
Yeah. Can I know for which application that memory alloy is used in ISRO?
Okay, so currently we have developed a cryogenic temperature sensor for ISRO-related application. It was, in fact, it was a funded project.
That's okay. ISRO, where it is used?
It is used in their...
Is it confidential or it can be told?
So actually, some information I got from them, probably that I can share. So it is for liquid hydrogen tank, for monitoring the temperature in a liquid hydrogen tank.
Okay. Since almost the session is in end, I just wanted to tell a very nice anecdote. When I was studying in Tata Institute, I finished my ME and then I was there searching for a job. At that time, my senior, the very famous figure, Nandini, from ISRO, had come to Tata Institute. And he saw, we said, hello. Then he said, Prasanna, come over to Tumba. We want to do start a separate section for material, this one at the time, that is 1968-69. Then Dr. Satish Dhawan, who was the director of the Institute of Science and also involved in ISRO, Nambinarayan and myself, and one assistant professor from Tata Institute, we had a discussion for 2-3 days to start a materials laboratory.
Okay.
At that time, I wanted to do a one-man upmanship, and the next day I took a wire and then say, I love you, I put it, and then crushed it, and then I showed them by heating it, it became I love you. You remember, that is a memory alloy. Then I was also a foundry student. I told I can do a lot of foundry and other things. But that thing fell through because of some other personal considerations. So it's still, I mean, now it is a different application. That's why I want to know whether they are still stuck up at the same age and thing.
No, actually, sir, like one is the one what we had working is fine. Apart from that, now for ISRO, we are developing a deformable mirror. So ideally for deformable mirror, so there is an actuator which is required. So what we are trying to do is, we are trying to make a shape memory alloy based deformable mirror on a large area, close to around 30 centimeter by 30 centimeter area, so that we create a origamic structure to it. And when we try to actuate it, we can have a deflection. So that work is in collaboration with Ahmedabad Center, SAC Ahmedabad Center.
So I was only wondering whether you are trying to open it up for all the public, so whether it is anything connected with it and that thing. Thank you.
Thank you. Thank you very much, sir.
Thank you.
Thank you.
Thank you very much.
So
Any other?
We discuss. I think there is one
it can
last
be done.
Myself Vinayak from Epirog.
Nice.
Is this compatible, as you told, it's for hydrogen application. So is this compatible for all fluids? Means water?
Yeah, we have tested with liquid hydrogen, liquid helium, liquid oxygen, and liquid nitrogen.
And how about the manufacturing wise cost impact in comparison with existing sensors?
Okay. See, actually on a lab scale, for fabricating this sensor, so it costed us close to around 300 rupees or something like that, because we have completely established this technology and we have developed the complete fixture for coating it on an optical fiber. Okay. So if we have an industry partner, we can take it up further. So the main motto is to compete with the commercial sensors.
Okay, thank you.
Thank you. Thank you very much for the opportunity.
Thank you very much. Team IIT Indore, please, hold on. We need to felicitate you. I would like to request Dr. Giridhar from BMS College to do the honors.